So the term texture is used to describe the size, shape, and arrangement of the mineral grains within a rock. Texture is also a characteristic used to classify igneous and sedimentary rocks, as we have seen in the past few chapters. So let's not get confused by that. And these type of rocks, which are metamorphic, will either have foliated textures or non-foliated textures for the most part. Most igneous and sedimentary rocks textures have a uniform texture, as we have seen, where most of the grains appear not to be oriented one way or another, but to be rather random. Metamorphic rocks, on the other hand, are going to present a preferred orientation of certain grains within that rock, or at least those metamorphic textures that contain the platy minerals like micas, such as muscovite and biotite, or elongated minerals like amphiboles, as you have seen. So this preferred orientation of those minerals typically exhibits the grains to be parallelly or subparallelly aligned to one another. The appearance of these rocks containing the elongated minerals varies from the point of view at which you're looking at the sample. So, for example, if you take a box of straws that you bought at the store and you look at said box from the opening side of the box, you're simply going to be seeing the circles that the straws make through the part where you suck the fluid out of them. But if you were to look at the box from either of the two sides that are not the opening side, then you're going to see the stick-like features that the straws make, which is what they are. So the angle of perspective is very key when you're identifying these foliated textures. So a metamorphic rock that exhibits this preferred orientation of its mineral constituents is again going to be said to possess foliation. Okay, so if it has that preferred orientation, it will have foliation. So the term foliation refers to any planar or nearly flat arrangement of those mineral grains or crystals within a given rock. Although foliation can also occur in igneous and sedimentary rocks, given the statement I just made, it is a fundamental characteristic of the metamorphosed rocks that have been strongly deformed for the most part. And this deformation, as we will see later, is mainly caused by folding and as we saw previously from differential stress. So this deformation is driven by the compressional stress, which we saw in the last few slides, that shortens rock units, causing mineral grains of pre-existing rocks to develop parallel or these nearly parallel alignments. So examples of foliation include alignment of platy minerals through rotation, include recrystallization, include the flattening of mineral grains or pebbles, and we'll go through all of these in a little bit more detail. Foliated textures include cleavage, which is where rocks can be split into tabular slabs, and it can include compositional bonding, where you have the separation of light and dark minerals showing a layered-like appearance. So most of the rocks are going to have cleavage, and then gneiss, which is a different type of rock, towards the end of the foliated foliated textures grade of metamorphism, are going to have the compositional bonding. So those metamorphic rocks that do not exhibit foliation are typically just named non-foliated textures. In this case, the rocks will not have a planar arrangement of those mineral crystals, but they will be rather random and disorganized. There are diverse ways in which foliation can form, as I mentioned in the last slide. So here we'll go ahead and go through them. The first one that we'll look at is the rotation of platy mineral grains. So in this case, the mineral grains themselves align nearly perpendicular to the direction of maximum stress, as can be seen in the image on the right side of the slide. This type of foliation formation takes place in low-grade metamorphic environments. Others are responsible for higher-grade metamorphic foliation, other processes which we'll look at now. So another mechanism is the recrystallization that will produce new minerals. So in this case, you're going to have the new minerals crystallize perpendicular to the direction of maximum stress. So remember that in recrystallization, you're going to have the creation of new minerals from pre-existing ones, like the creation of chloride that comes from the clay minerals that have been metamorphosed. Another mechanism of foliation is the flattening of spherical shaped grains. This mechanism can occur as distinct units of the mineral's crystalline structure slide relative to one another along discrete planes. So this ends up overall distorting the grains, as the figure above on the left is kind of showing you right here. So there's going to be a shifting of positions by the breaking of existing chemical bonds and the formation of new chemical bonds. Another way in which this flattening can occur is through a process where individual atoms move from a location along the margin of the grain that is highly stressed to a location that is less stressed. In this case, the position is going to change within the same grain. Again, from going from locations of high stress to low stress. So this is called pressure solution, and it is typically aided by the action of hot and ion-rich waters. So in this case, the outside ions will dissolve within those circulating waters, and they will later be deposited in areas of empty spaces, pore spaces, where there is less stress going on. Overall, this shortens the grains in one direction and will elongate them in another direction. In both of the cases of flattening, the mineralogy remains the same, and usually the targeted minerals are those that are more spherical in nature, like quartz or olivine or calcite, for example. So various types of foliation are going to exist, depending largely on the grade of metamorphism and on the mineralogy of the parent rock. The first foliated texture that we'll look at is the slaty texture, and we'll cover them from lower grade metamorphism to higher grade, by the way. So, slaty texture. So this type of texture forms for rocks that split into thin slabs when they're hit with a hammer, and when doing so, they appear to have a rock cleavage rather than a mineral cleavage. This type of cleavage is best displayed in the metamorphic rock slate, hence the name of the texture itself. But this slaty cleavage is also present in a few other metamorphic rocks. So slate, which is the rock after which the texture was named, as I said, is often used for roof and floor tiles, for example, in Scandinavian countries. The parent rock of slate is going to be shale or some other mudstones, and this is usually a low metamorphic grade rock. So the resulting rock has no visible grains due to its low grade metamorphism, and although it is a bit denser than its parent rock, which is shale, it is not too different in appearance, so many a times it's easy to mistake one for the other unless you weigh them, basically, because slate is going to be a little bit denser than its parent rock, shale. So the second foliated texture that we'll look at is phylitic texture. So I don't think that your book has phylitic texture as one of the textures, but we'll still go ahead and cover it here. So this is a low to medium metamorphic grade texture. So it is the next one that we'll look at after the slaty texture, meaning is the next one over in the metamorphic grade sequence. So in this case, there are still no visible grains to the naked eye, but the rock does present a sheen to it from the different mica grains that are within the rock itself. So mica grains, again, are muscovite and biotite for the most part. Remember that those tend to be pretty shiny, pretty glossy. So that's what gives it the sheen. Phyllite, which is the rock after which the texture is named, has that glossy sheen, and it has kind of like a wavy surface to it. But again, you still cannot see any mineral crystals without any sort of microscopic aid, or microscope or SEM or something like that. So again, as I said, phyllite is mostly made up of muscovite and also some chlorite crystals. So remember, chlorite comes from the recrystallization of clay minerals. And the parent rock for phyllite is also shale or mudstones. So basically a shale goes through metamorphism and it turns into slate first and then into phyllite. The next texture that we're going to look at is the schistose texture. So this is a medium to high grade metamorphic texture. In this case, the minute mica and chlorite grains in the slate and in the phyllite begin to recrystallize into larger muscovite and biotite crystals. So they're actually visible to the eye. So when these new minerals are large enough to be discernible with the unaided eye, they're going to exhibit planar or layered structures, which we call schistosity. Along with these mica crystals, schist typically display some quartz and some feldspar crystals as well that appear to be a little bit flattened or have lens-shaped kind of structures to them, and they tend to be embedded within the mica grains or surrounded by them. So schist is the rock after which this texture is named, and it commonly includes, again, micas and quartz and feldspars as well, maybe. Mica schists often also contain accessory minerals like garnet or staurolite or andalusite, for example. Sometimes they may also contain large quantities of chlorite or talc, which are both minerals formed from metamorphism, as well as those other three. We'll look at these a little bit later in the lecture, but those are all called index minerals, and they're characteristics of a specific metamorphic grade. And so chlorite and talc can be common when the rocks of basaltic composition undergo metamorphism and turn into schist textured rocks. The parent rock to schist is also typically shale, but with basaltic composition rocks that undergo metamorphism, obviously the parent rock is going to be basalt or mafic igneous rocks for that matter. Alright, so this is our last texture within that sequence of foliated textures. This type of texture forms under high-grade metamorphism, and it occurs when ion migration results in the segregation of minerals as it is shown in the image above. So there is a segregation of these minerals into dark and light-colored layers, which gives the rock the banded-like appearance, which we call a gneissic texture or gneissic banding. So gneisses do not split nearly as easily as schists do, even though they are foliated. Gneiss, which is the rock after which the texture is called, has that banded appearance of light and dark minerals. The most common minerals are quartz and feldspars within there, but you can also have some micas and some amphiboles. Most gneisses split in irregular forms, so again, they're not going to split through those weak planes through which you have foliation. And many a times, gneiss shows evidence of deformation within faults, for example, and sometimes faults as well. The parent rock, of gneiss is going to be granite, or it could be its phonetic equivalent, which is rhyolite, but it could also be a sedimentary rock like arkose or quartz sandstone that contains a little bit of, or not quartz sandstone, I should say, lithic sandstone, for example.